Okay, so we are going to do test of hypothesis using R. We have already learned the theory, most of the theory. So here I am working with the faraway package, and I will illustrate a number of ways using which you can carry out hypothesis testing using linear models. So what I first do is I load the package faraway, and I am going to use the data set called GALA for Galapagos. It has various things: species, endemics, area, elevation, nearest, cruise, and adjacent. Now I am going to fit a model. So this particular example is taken from the book, so I am just imitating their thing. You can find it in chapter 3. So what I will do is I will fit a linear model on the response variable species on everything except the endemics variable. So I can write it, instead of listing all the things, I can just write it by putting that dot minus endemics, the way I have done. So I will fit that model, and then I want to see whether area, that regressor area, is of any importance or not. So I will fit a model without that thing also. So I have got the two models: the general model fit, which I assume is a correct fit, is a good fit, and fit not, which is the restricted model. Now I can do those things: RSS not minus RSS, etc., etc. Now R already has a built-in feature for doing that thing for us. It is called ANOVA. So this function ANOVA will do this thing for us, ANOVA function. And if I write it in this way, so first I will write the restricted model, and then I will write the general model. So the restricted model followed by the general model, and I just execute it. You will get this output. It has the degrees of freedom and the two RSS. It also says what are the two models, the model 1 and model 2. So in the first model, this is somewhat badly written. It says that everything minus endemics, and in the second thing it lists everything, then subtracts in. Okay, so model 1 is the restricted model and model 2 is the general model, and it will carry out the thing. So this one is your RSS naught minus RSS, and this is the difference in the degrees of freedom, and they are dividing it by the appropriate thing. So they are getting this F statistic and the corresponding p value of the F statistic, which is the probability that you will exceed this observed value if the null hypothesis is true. Since the p value here is, say, greater than 0.05, I will say that I am accepting the null hypothesis. So in this case I say that yes, you can drop area and the fit will not be much worse for that. Now this ANOVA function is a kind of stupid function. So if you do the following thing, that is, you write the general model first and the restricted model next, the ANOVA function doesn't object, and it just produces something very weird. It produces a negative degree of freedom, and the sum of square turns out to be negative. However, when it computes the F statistic, it takes the absolute value, which is also a weird thing to do. So eventually it gives you the correct answer when you look at the F statistic or the p value. But just remember that you have to specify the restricted model first, the null model first, and the general model next. Okay, so this is one when you have fitted both the models, both the null model as well as the full model. Now in many cases you do not want to do that. You want to fit only the full model and then specify your null hypothesis as some kind of linear restriction on the parameters. If you want to do that, in that case, the first technique is something that you have described in class. You take that restriction into account, create a new null model, actually fit that using R, and proceed like this. But most of the time you do not want to do that. You want to specify that matrix, you want to specify that null hypothesis symbolically into R, and want R to create your restricted model, fit it, and do whatever. Everything should be done inside. So if you want to do that, then you proceed like this. You have to load another package, that's car. So I will do that, and I will use a different data set. This is also from the package far away. It's called coagulation, and it has got two variables. The first one is a continuous one, that is the response, and the second one is diet. So if I just take a look at the things, so I will say summary coagulation. So you can see that diet has got 4 levels. So there are A, B, C, D, and coagulation is a continuous variable with mean, max, etc. And out of these things, A occurs 4 times, B occurs 6 times, etc. So you have this particular thing. So now suppose I fit this model. So it's a one-way ANOVA model, pretty simple stuff. I get this. Now I will just take a look at whatever is my fitted thing. I see that I have the intercept and diet B, diet C, diet D. So the model is actually mu plus alpha I plus epsilon ij, and there are 4 alphas. Not all of them are estimable. So as we already know, R will drop the first one. So diet A is dropped, which means it is forcefully set to 0 to make things unique. It's non-unique, so it has just put that restriction arbitrarily to give some particular least square estimator. And you have diet B, diet C, diet D. Now suppose you are interested in testing whether alpha for diet B equals alpha for diet C. So alpha B equal to alpha C, that's what you want to test. You can write it in this way. You can just write LHT, linear hypothesis testing, that's what I took from the car package. Then write down the model fit, something that you are declaring as a good fit. Then I can specify the hypothesis as a string, diet B minus diet C. Notice the way I am writing diet B, diet C. This name I am getting from the output of the LM. So inside my data, they were not called diet B, diet C. They were just called BC. So you have to look at how they are written inside their fit, and you have to use that name, diet B minus diet C. I have not specified anything, so this means it is testing diet B minus diet C equal to 0. So let's carry out the test, and you get this test. So here the degrees of freedom is 1, so it means it fitted the restricted model somehow. There are actually shortcut ways of doing it, that's what it is using. But effectively it is fitting the restricted model and doing that RSS naught minus RSS thing, and it is getting that F statistic, the corresponding p-value is this. Now it could also specify not just this but equal 5. So this will test diet B minus diet C is equal to 5. Here you can see that they have written the hypothesis as diet B minus diet C equal to 0. So if you do not specify the right hand side, it will take it to be 0. Now if I do that, then I will have diet B minus diet C is equal to 5. So model 1 is a restricted model, model 2 is the general model, and they have tested it, and this p-value you can see is very small, much less than say 0.05, so it is highly significant, and they have also given you that significance level is a triple star gives you the significance score. So in this case you reject it. So that difference is by no means 5. And if you look at the last time, I had p-value is 0.1588. So diet B is basically same as diet C. Now you may be interested in testing something like, well, so before I go into that, so I can show how you can do the same thing using just a matrix notation. So remember that you have got in this case 4 parameters. What are the 4 parameters? So let's quickly see the 4 parameters that we had here. So I will write phi $coef, sorry, I misspelled it, coef. So they are intercept, diet B, diet C, diet D. So I can write the same thing as a linear combination 0, 1, minus 1, 0. So 0 means I am not taking intercept, coefficient 1 for diet B, minus 1 for diet C. So diet B minus diet C, no role played by diet D. I can do the same thing. So that will also give rise to the same result. Now if you make any mistake here, like you make it something smaller or larger, suppose you forget that diet A is dropped and you put a 0 for that, you will get an error message which is not very clear. What it says, error in L times B, non-conformable argument. So you understand that they are internally storing the coefficient in B and your restriction matrix in L. Incidentally, this could be a matrix. Here I am giving only a row vector because I have just only one restriction to put. If you have multiple restriction, put one restriction per row and look up the help of this function and you will see how things behave. You can look up the help of LHD and you will see exactly how you specify all this stuff. Okay. Now suppose you are interested in testing whether diet A and diet B are basically the same. So alpha 1 and alpha 2 are same. Unfortunately, R has dropped this alpha 1 term. So how do you do that? Well, the syntax is rather weird. So you just assume as if alpha 1 is fixed to be 0. So when you are testing alpha 1 equal to alpha 2, you are basically testing alpha 2 equal to 0. So that is a weird syntax of R because you really cannot test alpha 2 equal to 0 in a meaningful way because that is not even estimable. But that's how you have to write it here. So I write LHT fit diet B. So if I just write diet B, I am basically testing that alpha 2 minus alpha 1 is equal to 0. So let's carry that out. So it has happily carried out the test and it says that I am testing diet B equal to 0. Remember, it is testing this under that additional restriction that diet A equal to 0. So effectively it is testing diet B minus diet A equal to 0. Anyway, this is just weirdness of the syntax, but the result that you get is perfectly meaningful and you get this. In fact, you can even test things like more weird things like diet B minus 2 times diet C equal to 0. So you can use this syntax within a string and you will get that. So it will carry out the test, diet B minus twice diet C is equal to 0. So because it has already incorporated that lack of identifiability into its model by dropping the redundant column of X, so alpha 1 has been forcefully set to 0. Now we are working in a full column rank situation, so you can specify whatever linear combination you like and it will happily test it. But your interpretation should be this. So never say that I have tested alpha 2 equal to 0. Remember, it is working under that restricted setup where alpha 1 is set to 0. So whenever you test using R that diet B equal to 0, you should report it as saying I am testing alpha 2 equal to alpha 1. Okay? So that is basically the thing that I wanted to talk about in this video. Please go through chapter 3 of our book as well as look up the help of LHT because there are some slight nuances here and there that I have omitted.